Hello students, welcome to the fourth lesson in this chapter. We have been studying the graphs of trigonometric functions. In the previous lesson, we looked at secant and cosecant functions, and we noticed that the domain and range are not always either all real numbers or some finite interval, right? There can be values where a trigonometric function is not defined, so we have to have some restrictions in the domain, and there are some vertical asymptotes at those points. And then we also noticed that the range of the secant and cosecant function did not include anything between -1 and 1, right? So there can be strange things. Okay, let us see what we get if we try to graph tangent function. We will start by evaluating the tangent function at the standard four quadrantal angles, and then we will go from there. Okay, if we need more information, we will try to recall more information. All of this is only going to be recalling. We are not doing something new here because we know these functions. All that we are doing right now is to apply them. Okay, let's say that's your unit circle, and the coordinates on the x-axis at pi over 2 or 90 degree, at pi, and at 3 pi over, right? Let us try to use that. And remember the definition of tangent. Tangent is y coordinate over x coordinate, the unit circle definition. That means when you evaluate this tan at 0, right, y over x, 0 over 1 will be 0, at pi over 2, pi, 3 pi over 2, and back to 2 pi, which is same as 0. Let us write this. Okay, at pi over 2, it will be 1 over 0, so that will be plus or minus infinity. Our previous experience tells us that typically on the two sides of the asymptote, so first of all, 1 divided by 0 means you are going to have a vertical asymptote at pi over 2. On the x-axis, pi over 2, you will have a vertical asymptote, and on two sides of that asymptote, the function will go to plus infinity on one side and minus infinity on the other side. That has been our experience with secant functions, and I'm saying that it will be the same thing with tangent also, or with any other trigonometric function, because when you go from one quadrant to another quadrant, these typically, okay, I saying, yeah, it's almost always the case. When you go from one quadrant to another quadrant, the sign changes. Tangent is going to be positive in the first quadrant and negative in the second quadrant, because the y x coordinate is negative, y over x will be negative. And so if it is plus infinity on one side, it has to be minus infinity on the other side. Okay, that's the reason. And then if you look at pi, it will be 0. If you look at 3 pi over 2, again minus 1 divided by 0, so it will again go to infinity and negative infinity, and at 2 pi it's back to 0. Okay, so let's first plot these values on the graph. So I have now taken my interval only from minus pi to pi. Okay, and you will see very soon why that is the case. Why did I do that? If that is pi, then halfway mark pi over 2 is here. And what values we have so far? And 0 is here. Okay, tan 0 is 0, we have this point, and tan pi over 2, there is an asymptote. Okay, so directly the next thing we have is this, a vertical asymptote. Okay, and then at pi again, we are back to 0, which actually tells me we did not consider the negative side. We only took from 0 to pi on the positive, then we went to 3 pi over 2 and 2 pi. Let us trace it back. Okay, what is 3 pi over 2? 3 pi over 2 is same as negative pi over, right? Clockwise 3 pi over 2, anti-clockwise 3 pi over 2 is same as clockwise pi over 2. So at negative 3 pi over 2 also, at negative pi over 2 also, you will have a vertical asymptote here. Okay, let me label these lines now. So at negative pi over 2 and positive pi over 2, there is asymptote, and at 0 the value is 0. So I can kind of get an idea what's going to happen here. It will go from infinity here to infinity here and through 0 in the middle. But I want some more information, right, to be more accurate. So I'll just write plus or minus infinity here. Some more information, where will I get? Let me try half of pi over 2. It's pi over 4. And then I can also look at negative pi over. Okay, let us do that. At pi over 4, 45 degree, tan 45 is 1, at y over x, 45 degree, equal. And at negative pi over 4, you can look at it different ways. The value will be negative 1 because tangent is an odd function. We talked about that earlier. Or negative pi over 4 is in the fourth quadrant where tangent is negative. Okay. However way you see it, you can, as long as you can recall the value or identify the value, we are good. Okay. So that's my point. At pi over 4, the output is 1. At negative pi over 4, the output is negative. So now you have to think of a graph. What kind of graph? Which is asymptotic to these two dotted lines and goes through these 3 points. We're getting an idea, right? And if you have been getting this idea, you are right. Okay, it will be asymptotic here. And smoothly go up and be asymptotic there again. Okay, this will be like one basic, what we call a cycle. And you notice that now the period is only from negative pi over 2 to pi over 2 because you got all values from negative infinity to infinity. Okay, everything is there, right? So what will happen after that? It will repeat. On the left side, it will repeat. The same graph will repeat again and again. That's the graph of tangent. All right. So let us now fill in these blanks over here. The domain of the function I will write over here. Is what is not included? Pi over 2, negative pi over 2, and so on, right? So all numbers except, I'll write like this, x such that x is not equal to odd multiples of pi over 2. No, we have seen this before, so I'll just write it and move on. You understand it. If you want to understand this notation or how we say odd numbers, you should watch the previous video. Okay. So domain is all real numbers except odd multiples of pi over 2, where you have asymptotes. The range is everything, interestingly. And remember, look at the graph and see it. Okay. You take all possible values from negative infinity to infinity vertically, and there is no break or anything in between. Okay, so all numbers. Range is all of them. The period is of length pi. Very important. Okay. Why? Because you got all values between negative pi over 2 to pi over, and and the graph is going to repeat right after that. It's going to be like that again. Okay. So that is the period, and asymptotes are where the function is not defined. So those are x equals 2n plus 1 pi over 2 for all integer. Right. Let us do some practice. Evaluate tan 2 pi over 3. Okay. Now, sometimes the practice problems you might wonder is not directly from what we did here. Okay, that was graphing. And this practice problem will be more about the tangent function. Okay, so at 2 pi over 3, we are here, where in the second quadrant. That means your reference angle is pi over 3 in magnitude, right? And for pi over 3, you have to, so that means this side is pi over 3, okay? And the coordinates at pi over 3 or 60 degree are 1 over 2 and root 3 over 2, right? But you are on the negative side, so it will be negative x side. So negative 1 over 2 root 3 over 2. So your tangent of 2 pi over 3 will be root 3 over 2y over x. It's negative. Okay. And similarly, tan of negative 3 pi over 4. So 3 pi over 4 is like 3 multiples of pi over 4, but clockwise. 1 pi over 4 will bring you halfway, 2 pi over 4 will be 90 degree, 3 pi over 4 will be here. So this is the angle negative 3 pi over 4. Okay, in your clockwise rotation. So clearly your reference angle is 45 degree now, pi over 4. So coordinates would be 1 comma 1, sorry, 1 over root 2 comma 1 over root 2 in the first quadrant, which would be negative 1 over root 2, negative 1 over root 2 in the third quadrant. So that will be negative 1 over root 2 divided by negative 1 over root 2 or root 2 over 2. Okay, that is 1. In the third quadrant, tangent is positive. You can see that here. Okay. Let us similarly graph the cotangent function. You can go ahead and do it and then check with me. Okay, I'll start writing here at 0. This time I know better. Okay, so I'm going to go to pi over 4, pi over 2, 3 pi over 4, and pi. We will see. Okay, if we then want to move to negative side or not. And look at the unit circle on the upper left and write the values. The definition of cotangent is the reciprocal of tangent or x over y. Okay. So at 0 radians, the point is 1 comma 0. So 1 over 0. So here it goes to plus minus infinity. Okay. At It's undefined, by the way. I keep writing this plus minus infinity, but you will see in textbooks written undefined. I hope you are very clear at this point, okay, what it means. It is undefined because it's not plus infinity or minus infinity. It's going to have both values, but on opposite side of that asymptote. Okay. I write plus minus infinity for that clarity, what it should be on what we will find in the graph. And at pi over 4, that's 45-degree halfway mark, where x and y coordinates are equal. So the ratio is 1, reciprocal of tan anyways. So that's 1. And at pi over 2, it will be 0. 0 over 1. At 3 pi over 4, now you're in the second quadrant. It will be negative 1. Because x coordinate is now negative, y coordinate is positive. So the ratio is negative. And at pi again, you can see it will be clearly positive and negative infinity. Now let us try to graph it. Or sorry, let us write this domain and range and stuff, and then we will graph it. To start with, domain, what am I missing from the domain? I am missing pi. That's where it is undefined, plus minus infinity. I am missing 0. It's not difficult to see that the next time it will be undefined is again at 2 pi, right? Because at pi over 2 the value is 0. So at 3 pi over 2 it will again be 0. So odd multiples are safe here. The problem will be now with even multiples at pi, at 2 pi, and so on. Okay, multiples of pi or even multiples of pi over 2. So the domain is all x except those which are multiples of pi, or 2 times pi over 2. In general, n pi, n is any integer. Okay, and as far as the range is concerned, we will get everything again, but I'll show you in the graph also in a second. For now, I just want you to see it, because if this is reciprocal of tan, okay. So when tangent goes to infinity, this will go to 0, and when tangent is close to 0, cotangent will go to infinity. So effectively, you will get everything again. Period is again pi, as you can see. From 0 to pi, it's taking all possible values from infinity to negative infinity. And the asymptotes will be now at x equals n pi. That's where the function is not defined. Let us try to graph it now. Okay. And you have the table with you in your notes. I'm going to write here from by recalling it. Okay. 0 is here, pi over 2 is here, pi over 4 is here, 3 pi over 4 is here, and then pi is here. Okay, let's see. We said that at 0 there is an asymptote. So on y-axis there's an asymptote now. Again at pi, I have another asymptote. And this time I'm going to write the equations without failing. X equals 0 and x equals pi. I have asymptotes. What values do I have? At pi over 4, it's 1. And at 3 pi over 4, it's negative 1, right? Uh, that's the same as the values of tan, by the way, because 1 and -1 have their own reciprocals, right? And at pi over 2, it is 0. Okay. Now think of a graph which passes through these 3 points and is asymptotic to both those lines. And you can see clearly it has to be asymptotic here, and then gradually move here, and then again gradually go down and be asymptotic down there. Okay, basically you can see the graph of tan but flipped over, and but also shifted. Another important point of view you can have here is that when you are close to 0, between pi over 2 and 0, you are in the first quadrant. So it goes to plus infinity. Between pi over 2 and pi, you are in the second quadrant where cotangent is negative. So it goes to negative infinity on that side. You can see it that way also. Okay. Let us look at, and this answers now all the things that I said earlier. Okay. The range is negative infinity to infinity. The period is pi. You have asymptotes at multiples of pi, and so on. Okay. Let us evaluate the value of cot at some other angles. At negative 4 pi over 3, pi over 3, 3 of them will make 1 pi. So negative 3 pi over 3 is there. 4 pi over 3 should bring you there. Right? So the reference angle is pi over 3. And at pi over 3, in the first quadrant, the coordinates are root 3 over 2. I do the opposite always. 1 over 2, root 3 over 2. So at negative 4 pi over 3, it is negative 1 over 2, root 3. Okay. And what is the definition of cotangent? X over y. And that is going to be negative 1 over 2 over root 3 over 2. That will be negative 1 over root 3, which you rationalize and write as 3 over 3. Okay. What about 11 pi over 6? 11 multiples of pi over 6. Pi over 6 is 30 degree. 6 of pi over 6 will make 180 degree. And 5 more. 3 more will make 270. 2 more will bring you here. So the 11 pi over 6 is here, which is in the fourth quadrant. Okay. And clearly its reference angle is pi over 6. And if you go to the first quadrant, pi over 6 is here, and its coordinates would be root 3 over 2, 1 over 2. So in the fourth quadrant, they will be, right them below here, coordinates would be root 3 over 2, the x will be positive, y will be negative, right? So this would be root 3 over 2 over negative 1 over 2, which is negative. Alright, let us do more practice. We saw the basic graphing and how to evaluate the tan and cotangent at some angles. Here are some other problems you might have to deal with. Okay. First is evaluating this tan and cotangent in the calculator. Tan you can do easily because you will find a button TA and tan. You just have to make sure you are in the degree or radian mode as needed. Okay. In this case, you have to be in the radian mode. But this is cot, and you won't see a cot button on the calculator. What do? course, you remember that's the reciprocal of tan. So that knowledge is useful here. Necessary, not useful, necessary. Okay. So on the calculator, you will punch in 1 divided by tan and then put the angle. Whatever value that gives you approximately. Okay. Round it up. Let me skip that. Next, determine the period of each function. Okay. And to determine the period here, we have to remember fundamental period. I didn't talk about that while graphing both tangent and cotangent. Fundamental period of tan and cot, both of them, is length pi. Okay, that's one thing. And the cycle, fundamental cycle for tan is negative pi to pi over 2 to pi over 2. For cotangent, it is 0 to pi. I should actually show that in a separate table. Okay, let me just leave it here boxed. Okay, this is one thing you might want to note down and remember it. A second piece of information I'm going to write on the top here. Okay, which is this fundamental cycles. Okay, of two things, tangent and cotangent. For tangent, you might want to see the graph quickly and be sure that you are you understand it carefully. Tangent is here, right, between negative pi over 2 and pi over 2. But at those points, there are asymptotes, so those should not be included. The end point should not be included. Similarly, for cotangent on the right side here, you can see it's 0 and pi. 0 on the left, pi on the right. Not including those, but in between. Okay. Hence, in my fundamental period, tangent is negative pi over 2 to pi over 2 fundamental cycle, and for cotangent it is 0 to pi. Okay, the length is pi in both cases. Okay, why is that needed here? Over here, the period will be pi over b, not 2 pi over b. Okay, where b is the coefficient of x. So in this case, it is pi over b is pi over 2. That gives you 2. Okay. In the second function, first you need to realize this can be written as 3 tan. You have to factor out that pi. Okay, becomes that when you write it in the general form, So the shift is 1 over pi, but the period itself is affected by that pi in the front of x. Okay. So the period now will be pi divided by that pi, which is 1. Okay. Those ideas, will be needed if you were to sketch the graph of those functions, which we will do for another example here. Sketch one cycle of the graph and 3 tan x, x is not modified, so the period does not change. Okay, the vertical asymptotes, where will you get them? Again, you did not change the value of x. Okay, no shifting, no shift, no horizontal stretching, so the period is the same. No horizontal shift, so the vertical asymptotes are the same again, which will be x equals odd multiples of pi over. Okay, and I will, this is important stuff, so I'm writing here. No horizontal stretching or shrinking, covers both, and no horizontal shift. Hence, the period and the vertical asymptotes are the same as your original tan function. Then what has changed? Not even the range. Okay, you think about it. Range is still negative infinity to infinity because multiplying by some number or subtracting some number doesn't change infinity to infinity, right? So that also remains the same. What will change is, so I will write that here. Okay, what changed? Okay, so what changed is this. Um, you can call it the average position or basically the horizontal line of symmetry. Okay, because you have moved it 2 units down, horizontal, I'll just call it midline, an informal language. Okay, it's not exactly average because this is from infinity to infinity. So I'll just call it midline. The line that is in the middle of the graph is at y equals -2. Okay, that's what has changed. And it has been vertically stretched. So it will be going to infinity and negative infinity 3 times faster. It will be more steep. I will write that maybe in informal language here. 3 times steeper vertically. With that understanding, let us draw the graph. So the new horizontal baseline is here. Okay, at -2. And actually I should not do dotted for that. Let me do solid. This is your midline, and your asymptotes are still at odd multiples of pi over 2. So let me go ahead and mark them. Negative pi over 2 here, positive pi over 2 here. Okay. And then the asymptotes. And some other values like 3 times steeper we said, right? And this is your new baseline, so 0 will be there. Actually, you can plug in and check. If you plug in x equals 0, you get 3 times tan 0 minus 2. So that will be 0 minus 2 minus 2. Okay, so your y-intercept is 0 minus 2. Maybe you can write it that way also. Y-intercept is 0 minus 2. Okay. Remember, the x-axis is here, y-axis is here, the origin is here, and we are 2 units down. And at 1, it will not be going just 1 unit up, it will be going 3 units up. Okay, at pi over 4. Here at pi over 4, you will be going 3 units up there and 3 units down here because it is 3 tan x. So your graph will now be no. I need to show I need to show it going to infinity faster. Like, okay. And on the left side, like this, to infinity faster. So it will look more steep, more like a straight line, but there is an inflection there. Okay, like that. Okay, that is one cycle. Similarly, let's do the next one. Sketch one cycle, and here some things change. Okay, now the periods will change because this is cot 3 times x plus pi over 3 plus 2. Okay, so your period is now pi over 3 because of the 3 here. And your vertical asymptotes will also shift because you are doing x plus pi over 3. So phase shift, right shift, or what you call phase shift, is right shift up, left shift actually, my bad, because it is x plus pi over 3, so left shift of pi over 3 units. Okay, so in the graph what you have to do is this: pi over 3 left shift. So say this was 0, you take this as, and the period itself is pi over 3, right? So take this as pi over 6, negative pi over 6, and make this as negative pi over 3, and 0 here, pi over 6, pi over 3. So from 0 to pi over 3, it would complete one cycle, and negative, between negative pi over 3 and 0, it will complete one cycle. Okay, so I'm showing that. And there is plus 2, so vertically it has shifted up, which means your mean position now will be here on the line y equals 2, the midline. Okay, and what else can you do? And it has been vertically again, not vertically, horizontally, because the period is pi over 3. It's horizontally shrunk. Vertically, you didn't multiply the values there, so that's fine. That's not vertically stretched, but shifted up. Okay, all of that is now taken into account. So what will be the values? As x approaches 0, okay, you will be at cot pi, and cot pi is infinity. Okay. Mm, mm, mm. To get a precise one, now we know where the asymptotes are. Okay, the asymptotes are here at 0 and pi over 3. And how do I know that? Because the period is pi over 3 now. So the fundamental original period was 0 to pi. This will be 0 to pi over 3. Okay, so your asymptotes are here. But where is it going to plus infinity and where is it going to minus infinity? For that, you have to understand that whole graph has been shifted, right? As a result, you might directly be able to see it is negative here, it will be 0 in the middle here. I should show it decreasing because I have not changed the direction. Okay, let me do one thing. Let me evaluate it at some values. Okay, that is more reliable. At 0, I am doing cot 3x plus pi. Okay, at 0, the value is cot pi, which is plus minus infinity. But at pi over 6, it will be cot 3 pi over 2, and cot 3 pi over 2 is 0. So here the question is, are we on the positive side or negative side? Okay, so when x is 0, you are little bit more than pi, that is third quadrant where cotangent is positive. Okay, so the graph will look like this. It will go decrease from there, and I'll explain in a second more. Okay, why I say now it should be like that. Like that will be the graph. Okay, so one way to see this is the same as the graph of cot x, but with period shrunk by factor of 3, and whole thing has been shifted by pi over 3 again, as you can see here, by pi over 3, but it's periodic, right? It keeps repeating in those blocks. So between 0 and pi over 3 you will get this graph. If you go to the left side, you'll get this graph. Okay, now it's easy to sketch it. You'll get that on the between negative pi over 3 and 0. The line, okay, let me change its color so you can see it. The midline being y equals 2. Okay, there's one last thing I will say here. How do I know that, it is infinity, plus infinity here and minus infinity here? That is, when I'm here, okay, x is going to 0, very small x, but positive 0, right? We call it 0 plus, okay, just to indicate that it is the values of x a little more than 0. As a result, 3x plus pi will be a little bit more than pi, because x is a little bit more than 0. Okay, that plus on the like in the exponent indicates that it's more than pi. Okay, x is a little more than 0, so 3x plus pi is a little bit more than pi. That more than pi or less than pi is important because we need to know the quadrant, which is quadrant 3, and in quadrant 3 cotangent is positive. That's how I know it is plus infinity here. Okay, and similarly you can figure out why it will be here, going to negative infinity on that side, or you can just see that it's one cycle, so it has to be going to negative infinity. Okay, there is a lot to understand there. Take time, think about it more. Here is another question. Now reverse engineer. Look at the graph and write the equation. What do I see? I see that this line here is pi over 4, mark pi over 4. Okay, that means over here is pi over 2 and over here is 0. So the normal graph of tangent is from 0 to pi, minus pi over 2 to pi over 2. Okay, the fundamental period. But this one is from 0 to pi over 2, which means you can see that it is horizontally shrunk 2 times. So the value of b is 2. Okay. Then I noticed that my original tan, because of the shape is like the tangent, I'm thinking in the tan point of view. The tan goes like that through 0, right? But this is shifted to the right. So there is a right shift which will be subtracted. So value of c will be pi over 2. Okay. What else? I will get the value of, like, maybe, and okay, one more thing, D. You can still see the baseline has not changed, still changing the value at 0, that is the x-axis, and the graph is symmetric about that. So which tells you D is 0. Only thing remains to be determined is A. And for that we can do this. Okay, I will write the equation down first. The equation will be y equals A tan B is 2, x minus c is pi over 4, plus d is 0. Okay, you can simplify it. That will be A tan 2x minus pi over 2. That is the equation. When you simplify it, in the form, given form, this is the like, as you are asked to put it. Okay, I simplified it because I want to find the value of A. How do I get that? That's a point given, 3 pi over 8 comma 1. Okay, I am now going to continue here at 3 pi over 8 comma 1. Your equation will be y equals, so 1 equals A tan x is 3 pi over 8. So 2x will be 3 pi over 4 minus pi over 2. Okay, now simplify that. 3 pi over 4 is 135 degree minus 90 degree. So which is basically 45 degree, or tan pi over 4, which is 1. So A times 1 is A, which means the value of A is 1. Okay, hence you can replace this by 1, and that will be your answer. Y equals tan 2 times x minus 4. Okay. Here, a small note I wanted to make. We have been looking at the graph of tangent, and that comes in the context of equation of a line. Okay, why? Because we say the equation of a line can be written like that, mx plus b or mx plus c, where m is the slope, right? And a small note about that I wanted to make is, if you look at any line, okay, let's say it makes angle theta here with the x-axis, the slope that we are calculating is change in y over change in x, right? But isn't that the definition of tangent? Okay, so it turns out this m that we use in the slope of the line is tan theta, where theta is that angle with the x-axis, which is exactly called the inclination. Okay, this theta is the inclination and m is the slope. Okay, let me take a pause here. We switched the gear here suddenly. Okay, I should have warned you about that. So we did the graphing, we're done. We're looking at another concept of this tangent functions. Okay, and this you can say is an application, and the application is the tangent of the inclination is the slope of the line. Okay, and the connection is, for you to understand, is the definition of tangent as y coordinate over x coordinate. Okay, so this equation here, m equals tan theta, is something you might want to memorize. Okay, so here's the question. Find the equation of a line through 1 minus 2 with an inclination pi over 3. So that means your slope m is tan pi over 3 which is under root of 3, and the point is 1 comma minus 2. So 1 y minus y1 equals m times x minus x1. Plug in. You get y plus 2 equals under root 3 x minus. Okay. Write the equation of the curve in its final position. The graph of y equals cot x is shifted pi over 4 units to the right, stretched by a factor, and then translate. Relatively simple. Okay. Write your answer. We have done this kind of activity in the previous lesson also. Shifted to the right. Okay, so that will make it cot x minus pi over 4 stretched by a factor of 2 and then translated to units down. Okay. The point 0, 0 on the graph of tan x. Okay, this is another very important concept question. For this, I will take you back to the graph of tan x. Okay, be attentive. We have not talked about this before. So the graph is this tan x, right? And you observe something here. Before, on the left side of 0, this is down, right? We talked about that concavity concept earlier. This is concave down. And after 0, if you see, it is facing up, concave up. Look at the shape of the graph. It's down and then up, facing down, facing up, right? Concave down to concave up. Where does the change take place? At 0. Okay. Such a point where the inflection takes place, the concavity changes, it's called an inflection. Okay, as a reminder, I will just draw a quick graph here like that. It changes from concave down to concave up. Okay, that's inflection. Okay. Similarly, the dot 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 of y equals tan x is the set of all real numbers except the numbers of the form that where k is an integer. Okay. So where except means we are talking about restricting something, so that's the domain. The domain of tan x is all numbers except where you have 90-degree or multiples of that, right? Odd multiples. So that was 2n plus 1 pi over 2 or 2k plus 1 actually, where k is an integer. And finally, the probably we're talking about domain again. Okay, the domain of cot x is the set of all real numbers of the form except the numbers of the form k pi where k is an integer. And these two things here, tell you that the graph of tangent and cotangent are shifted by pi over 2, the phase shift, the phase difference we say it, This is the terminology you'll hear in some real world applications. We call it phase difference or phase shift between tan and cot is pi over 2, just like that is between sine and cos, sine and cosine, phase difference is pi over 2. Secant and cosecant, the phase difference is pi over 2. Tangent and cotangent, the phase difference is pi over 2. As you can see here, when we talk about these asymptotes, right? Where, the values where it is not defined, they differ by that pi over 2. odd multiples of pi over 2, even multiples of pi. Okay. With that, I will wind up this lesson. I'll see you in the next one. Thank you.